Welcome to an exploration into designing notification systems that can confidently operate at massive scale. Today, we're diving deep into the architectural patterns and crucial strategies that enable services to achieve incredible delivery rates, often 99.99%, even when processing over 10 million notifications per second. We'll uncover how leading companies tackle the inherent complexities of distributed notification delivery. Consider the infamous silent killer scenario. When Instagram added likes, they hadn't fully anticipated a single high-profile post, like one from Cristiano Ronaldo, triggering an avalanche of 50 million notifications almost instantaneously. This sudden deluge completely overwhelmed traditional push systems, leading to database connection exhaustion, mobile carrier throttling, and user notifications arriving hours late or not at all. This catastrophic event vividly illustrates the core challenge. It's not merely about sending a notification, but orchestrating millions of unique deliveries reliably across diverse channels, all while adhering to user preferences, rate limits, and critical priority levels without causing a system-wide meltdown. At the heart of scaling notification systems lies the fan-out problem. Naively broadcasting notifications, where a single event directly generates individual messages for all recipients, is a surefire way to cripple your infrastructure. Imagine user A, a celebrity with 10 million followers, making a post. If your system immediately tries to create 10 million distinct database records or dispatch 10 million direct messages, your databases will face an overwhelming write storm. This massive concurrent write load quickly exhausts connection pools, causes deadlocks, and leads to severe performance degradation or even outright system crashes. The system struggles to keep up, not because of network capacity initially, but due to the sheer volume of data operations. This thundering herd problem isn't just about databases. It can also overwhelm message queues, API gateways, and even external service providers if not managed correctly. Understanding why this naive approach fails is the first step towards building resilient, scalable notification architectures. The breakthrough in solving the fan-out problem is to decouple notification creation from immediate delivery through a staged fan-out approach, combined with strategic priority queuing. Instead of instantly generating every individual notification, we first persist the core event, like user A tagged photo X, into a write-ahead log or wall. This single atomic write reduces immediate database load. Then, a lazy fan-out mechanism takes over, generating individual notifications on demand during reads or via background jobs, spreading the load over time. Critically, we introduce priority lanes, routing high-priority notifications, such as security alerts or payment confirmations, through dedicated queues with reserved processing capacity. Slack, for example, uses a three-tier system: P0 for critical direct messages with dedicated workers, P1 for important channel messages using 80% of the worker pool, and P2 for low-priority items like marketing, which only utilize spare capacity. This sophisticated prioritization ensures critical alerts are never starved by less urgent, high-volume notifications, maintaining system stability even under extreme load. To prevent overwhelming users and external channels, robust rate limiting is essential. The token bucket pattern is a widely adopted strategy where each user or channel has a budget of notifications, for instance, 50 to 100 per hour. When this budget is exceeded, suppression logic kicks in. LinkedIn employs a sophisticated sliding window algorithm. If a user receives too many notifications within a specific time frame, the system dynamically groups similar alerts, such as John and 47 others liked your post, or delays non-urgent notifications by 5 to 15 minutes. This isn't just a fallback, it's a critical feature. This digest mode transforms a potential flood into a concise update, significantly improving user experience by reducing notification fatigue by 70%. Crucially, it also delivers substantial infrastructure savings, often decreasing load by 60% by minimizing individual sends. Effective rate limiting, coupled with intelligent aggregation, balances immediate delivery with user well-being and system resilience. In distributed notification systems, achieving exactly once delivery is prohibitively expensive and often impractical at scale due to the inherent complexities of network partitions, retries, and distributed transaction semantics. Therefore, systems typically aim for at least once delivery. This means a notification might be sent multiple times due to retries after transient failures, but it guarantees that the message will eventually be delivered. The challenge then becomes handling potential duplicates on the client side without confusing the user. The solution lies in item potency tokens. Each notification carries a unique identifier, like user123, event, photo tag ABC789. When a client receives a notification, it checks this token. If it has already processed a notification with the same ID, it simply ignores the duplicate. WhatsApp masterfully uses this pattern. During network hiccups, you might technically receive the same message packet twice, but the application intelligently displays it only once, ensuring a seamless user experience despite underlying delivery complexities. This approach balances reliability with operational practicality. Twitter's notification architecture provides a compelling real-world case study in scaling. Initially, they relied on a simple pull model where clients periodically fetched timelines, leading to resource wastage and high latency, often a minute or more. As their user base exploded, this became unsustainable. They evolved into a sophisticated hybrid push-pull model. For active users, those active within the last 5 minutes, they utilize push notifications, ensuring near real-time updates. For less active users, they revert to a pull model, fetching updates when the user next engages. Crucially, they adopted different fan-out strategies. For regular users with fewer followers, under 5,000, timelines are pre-computed using fan-out on write. However, for celebrities like Justin Bieber with over 100 million followers, fan-out on read is employed. His tweets aren't pre-distributed to every follower's timeline. Instead, they're fetched on demand when a follower actively views his profile or timeline. This intelligent hybrid approach dramatically reduced infrastructure costs by 40% while improving latency to under 100 milliseconds for 99% of users. In designing at-scale systems, anticipating and mitigating failure modes is paramount. Firstly, dead letter queues or DLQs are essential. After a few retry attempts with exponential backoff, notifications that still fail, e.g. due to malformed data or deleted users, are moved to a DLQ for manual investigation, preventing poison messages from blocking main queues. LinkedIn found 0.001% of notifications failed permanently, highlighting the need for DLQs. Secondly, circuit breakers protect external channels. If an email provider repeatedly responds with a 429 rate limit exceeded error, the circuit trips, temporarily stopping requests to that provider for a set duration, preventing retry storms. Shopify saw a 90% reduction in wasted API calls after implementing these. Finally, graceful degradation is crucial during peak loads or outages. During events like Black Friday, Amazon's system automatically disables marketing notifications, delays non-urgent alerts, and increases digest grouping thresholds, while ensuring critical notifications like order confirmations maintain full capacity. These strategies are not just for recovery, they are fundamental to proactive system stability. To truly grasp these concepts, hands-on experience is invaluable. We've prepared a comprehensive demo that allows you to build and observe a production-grade notification system in action. This demo implements several key features we've discussed today. Multiple delivery channels including email, SMS, push, and webhooks. A robust 3-level priority queuing system. A user-specific token bucket rate limiter to manage notification floods. Sophisticated retry logic with exponential backoff to handle transient failures. And a crucial circuit breaker mechanism to protect against external API overloads. Furthermore, it includes a real-time dashboard that provides immediate insights into throughput, latency, and failure rates, allowing you to visualize system performance under various loads. The working code simulates 1,000 notifications per second across 100 users, each with varying priorities. vividly demonstrating how the system maintains stability, respects rate limits, retries on failures, and ultimately ensures successful delivery, all in real time. It's an immersive way to see theory applied. In conclusion, designing notification systems at scale is fundamentally about managing controlled explosions, not just sending simple messages. The sheer volume and diversity of notifications, coupled with the need for high reliability, make this one of the most challenging distributed systems problems. The most effective designs are proactive, focusing on preventing issues before they escalate. Mastering patterns such as staged fan-out for efficient delivery, implementing intelligent priority lanes to ensure critical alerts are never delayed, leveraging dynamic rate limiting and digest modes to enhance user experience and reduce load, and building robust failure handling mechanisms like dead letter queues and circuit breakers are absolutely essential. These principles allow you to architect systems that are not only capable of handling millions of notifications per second, but also resilient and cost-efficient. By understanding and applying these core patterns, you'll be well equipped to confidently tackle notification architecture in any system design challenge or scale your own applications to millions of users without experiencing notification-induced outages.